In this video, we will look at the k-means algorithm and a few important properties. We will begin with a step-by-step example. We will take 8 points in a two-dimensional space, annotated x1 to x8. For this example, we choose k equal to 3, so we want the algorithm to find 3 clusters. During the initialization step, 3 points mu1, mu2, and mu3 are chosen at random. They represent the centroids of the 3 clusters that the algorithm is going to build. The first iteration of the algorithm will begin by assigning each point to the cluster with the closest centroid. For x1, the distance to mu1 is approximately 5.39. The distance to mu2 is 5. And the distance to mu3 is approximately 8.06. Mu2 is the closest of the 3, so we assign x1 to the cluster C2. Similarly, x2 is closest to mu2, so we also assign it to the cluster C2. x3 is a special case because it is equally close to mu1 and mu2, but it cannot be in 2 clusters at once, so it will be randomly assigned to mu1. And so on for each point from x4 to x8. After all points have been assigned to clusters, the first step is complete. In the second step, these clusters are used to update the centroids. To calculate the x-coordinate of the first centroid, we average the x-coordinates of the first cluster, which gives 5, and the y-coordinates of the first cluster, which in this case gives 4.25. So mu1 will be now placed at these coordinates. We use the same method to find the location of the second centroid, mu2, and of the third centroid, mu3, which, having a single point, is the same as x8. This is the end of the first iteration. The 2 steps are then repeated in the second iteration. Again, the clusters are created using the distance to the nearest centroid, so points x1, x2, and x3 belong to the C2 cluster, x4, x5, and x6 to the C1 cluster, while x7 and x8 to the C3 cluster. Note that the clusters are slightly different from the first iteration. Then in the second step, the centroids are updated again. mu1, mu2, and mu3 are updated as before. The third iteration begins and the clusters are updated for a third time. But this time the clusters are exactly the same as in the previous iteration, so the algorithm stops and returns the current set of clusters. The J criterion. Since the final clusters depend on the random initialization of centroids, a way to compare different results is needed to help the algorithm choose the best one. For instance, these points could be clustered like this, which looks odd since x4 is a bit far from the other 3 green points, or like this, which looks more natural. A useful function to compare the 2 sets of clusters is the sum of squared distance between each point and its corresponding centroid, also called the J criterion or inertia. For example, in this configuration, we can calculate j as the square distance between x1 and mu1 plus the square distance between x2 and mu1, and so on until x5 and mu2. Replacing the distances with the actual values in this case, we get approximately 5.34. For the alternative configuration, we get approximately 24.78. So by choosing the clusters with the lowest value of j, we get a more natural set of clusters. This direct comparison, however, only works if the two configurations have the same number of clusters. But this function can also be used to choose the value of k in a more indirect manner using the elbow method. We can keep track of the j criterion after running the full algorithm for each possible value of k. So for k equals 1, we get 151. For 2, we get 42.67, and so on, until k equals 8. By plotting these values on a graph, we can see j sharply decreasing in value until k equals 3, after which the values no longer improve significantly. This marks the elbow of the graph, which corresponds to the most natural number of clusters. In this case, it is easy to check just by looking at the graph that indeed we have 3 distinct clusters. But if the points had more than 2 dimensions, or there was a very large number of them, the visual representation would have been much more difficult to interpret. Voronoi diagrams can sometimes be used to speed up the calculations. The first step of the algorithm involves calculating distances between each point and each centroid. But in the particular case of a small 2D dataset like this one, we can solve manually using a visual method. Instead of calculating the distances between each point and each centroid, like we would normally do, we can just separate the zones that are closest to each centroid by using a Voronoi diagram for the centroids. First, we plot a line between mu1 and mu2 and draw the perpendicular through the midpoint. We repeat the process for mu1 and mu3 and for mu2 and mu3. We now remove the parts of the perpendiculars that are closer to another point than the points that formed it. So, for instance, this segment is formed by the mu2, mu3 perpendicular, but is closer to mu1, so we remove it. Similarly, we remove these 2 segments, and we are left with 3 distinct zones which contain all the points for our 3 clusters. Note that these 2 points fall exactly on the edge between the first and second cluster, so we will arbitrarily assign them to the first cluster. This method is, of course, imprecise, and points very close to the border should still be clustered using distance calculations. We then continue with the second step of the iteration as before. I hope this has been useful, and please check the links in the description for additional references. Have a nice day!